Greetings, peeps. An important quantity that works intimately with momentum is known as impulse. Impulse is defined as force times the change in time, but really what it means is the amount of time a force is in contact with an object. So it's the average net force acting on an object during a time interval. The symbol for momentum is J. I don't think we've used J for symbols yet. Nope, that's available. Totally cool. By itself. We've used J to notify the unit joules, but not as a symbol yet. It's also a vector. Force is a vector, therefore impulse is a vector too. Its unit, not surprisingly, newtons times seconds. Newton seconds. An impulse will create a change in momentum. So F net times delta t equals delta mv. So the change in momentum. Now let's consider if m is constant for a moment. M is constant. So we have F net times delta t equals m delta v. We rearrange this, we divide both sides by delta t, and we get something quite familiar. F net equals m delta v over delta t. Well, delta v over delta t is actually linear acceleration. This is F net equals ma, Newton's second law. Newton's second law of motion was originally presented in terms of the change in momentum. That's how he originally wrote it. So that's really kind of cool. It was later adapted as F net equals ma, just a little easier to use, with the assumption that mass is going to be constant. And in fact, mass doesn't have to be constant. There are things like, well, rockets. Rockets lose their mass by expending lots of fuel, and so we have a change in momentum that would also involve changes in mass and in velocity too. All right. So the overall equation looks like this. F net equals m. The change in momentum with m constant is, of course, delta v, which is v final minus v naught over delta t. Next, we'll look at some real-world applications of impulse and momentum. Hold on. Alright, so let's check out some real-world applications of impulse and momentum. So, first, check it out. What if the object starts at rest? So we got v naught equals 0 meters per second. What's the condition there? What kind of variables do we look at here about getting this object so that Vf is maximized? Great English there, but you know what I mean. We want to figure out what variables can help us maximize velocity. Well, we rearranged the equation to solve for Vf. And we have this, F net times delta t over m. So if we start off with a small mass, because in the denominator, we can accelerate it easily. It'll have less resistance to changes in motion, so we can maximize our Vf by having a small mass to begin with. Sometimes you don't have that luxury, but if you have one, that's one way to get the object to be moving at maximum velocity. How about this one over here, F net, a large average force? That's pretty intuitive. If you have a large force, large push or pull on this object, you're also going to change its velocity and maximize it after this impulse. Here's the one that we haven't dealt with. We're now connecting force and time together, which we really haven't done directly. So delta t, what this says is that if we have a large contact time, in other words follow through, in cases of sports, so if you have a large contact time, you're also going to increase Vf. So in sports, pretty much, you are trying to follow through if you're accelerating an object. So a slap shot or a wrist shot in hockey, or swinging a golf club, or even a bat or a throw of a ball. And tennis, all the sports involve this, where if you want to maximize Vf, you actually have to make sure that you follow through to ensure good contact time. Let's take a look at another situation. Scenario. What if object has velocity, but then has to come to rest? Okay, we want it to stop. Where Vf is 0 meters per second. Now what do the variables say about reducing the impact force that's acting on the object? Well, we've solved this now for F net, but with V final is 0. So we got a negative force. In other words, the force vector has to be opposite that of motion, opposite that of velocity. That's important. And it equals negative m v naught over delta t. So what we can do is, if we started with an original velocity, this is easier. We can limit the impact force if we just don't have an object moving very fast. That's good. and it doesn't have much mass. That's also good, right? Sometimes you have no choice. Sometimes the object has this momentum here, a certain m and a certain v, and you want to try and limit the impact force. Then what do? Well, you try to increase this time because it is in the denominator. If you increase this value, the overall value here goes down and force net goes down. So to change velocity, you have to have a little give. So again, in sports, if you're receiving a ball in soccer, you try to trap it, you want to have a little give. If you are catching a ball, you have a little bit of give in your glove. Your glove also does some of that in baseball, for example. If you are jumping off of a table, don't do it stiffly, a gymnast, okay? Gymnasts, they try to do this, but it's very difficult, okay? You want to bend your knees so that you lengthen the amount of time. It puts less stress on your body because it has some give. In terms of everyday objects that we use, automobiles, airbags. Airbags inflate and they create a cushion so that your head doesn't just slam into the windshield or a steering wheel if you're sitting in the front. Instead, it has a little bit more time to slow down. Crumple zones do the same thing in front of the car. They maximize the amount of time. By maximizing time, you reduce the force of impact. And so that's what it is. Impulse momentum has lots and lots of applications in terms of everyday life, sports, automobiles, all sorts of things. And it's a very important topic in physics. That's what it is. Morad out.